Hi, I am Firyuza and you are watching Bold Science with Firyuza. Today we are diving into a fascinating and mysterious experiment that puzzles even those well versed in quantum mechanics. When people first encounter the paradoxes of wave-particle duality, they often start to wonder, were those experiments really interpreted correctly? Can an electron or a photon truly travel along two paths at once? Maybe the interference pattern comes from interaction between different particles, while each individual particle, as an individual object, actually follows only one definite path. To clear up these doubts, let's look at the Mach-Zehnder interferometer experiment, where interference effects appear even when just a single particle is involved. The Mach-Zehnder interferometer is one of the clearest setups demonstrating quantum paradoxes. At first glance, it's a simple optical arrangement: two beam splitters, two mirrors, and two detectors. Yet it challenges the classical notion of a particle having a well-defined trajectory. Today, we'll examine two versions of this experiment that you'll see on the screen. And step by step, we'll track exactly where classical logic breaks down. On the screen now is the first setup. A laser emits photons one at a time. Each photon reaches the first beam splitter, a partially transparent mirror. A beam splitter is a semi-transparent mirror that transmits a photon with 50% probability and reflects it with 50% probability. Photons leave the laser one at a time. Once a photon reaches beam splitter 1, there are only three logical possibilities. It travels along path 1, along path 2, and along both paths at once. If it takes path 1, it reflects off mirror 1. If it takes path 2, it reflects off mirror 2. The two paths then meet again at beam splitter 2. After that, the photon can be detected either by detector 1 or detector 2, but never by both at the same time. Each photon is always registered by only one detector. Now let's switch on classical intuition. If the photon is a particle, it must choose a single path. After the first beam splitter, it's as if the photon flips a coin, a 50% chance of going one way and 50% chance of going the other. Imagine it has already chosen its path and continues forward. It reaches the second beam splitter. That beam splitter again divides the beam in half, 50% toward detector 1 and 50% toward detector 2. If everything happens independently and fairly, 50-50 at each step, then in the end, half of all photons should reach detector 1 and half should reach detector 2. So equal detection probabilities are the natural classical expectation. Now let's move to the second setup. Here a glass plate is inserted into one arm of the interferometer. It increases the optical path length and introduces a phase shift. In other words, we are changing the optical path length of one arm of the interferometer. If the photon were traveling along only one route, changing the length of the other path shouldn't affect the outcome at all. But the experiment shows the opposite. As the thickness of the glass plate is varied, the distribution between the detectors changes smoothly. Fewer photons reach detector 1 and more reach detector 2. At a certain phase, detector 1 goes completely dark. Every photon is registered only by detector 2. As the path length continues to change, the situation reverses. Now detector 2 goes dark. And this happens even when photons are sent strictly one at a time. If the photon traveled through the first arm of the interferometer, how could changing the optical length of the second arm possibly influence its motion? Quantum mechanics answers this way. After the first beam splitter, the photon state is described as a superposition of two coherent components. What is a superposition? It means that after the first beam splitter, the photon has not selected a single definite path. It is described as existing in two possibilities at once, in the upper arm and the lower arm. This doesn't mean the photon has split into two halves. It means its state is described by two simultaneous alternatives, and it is precisely this feature that later produces interference. The photon doesn't divide into pieces in any classical sense. What interfere are not halves, but probability amplitudes. At the second beam splitter, these amplitudes combine, either adding constructively or cancelling each other out. The glass plate controls the relative phase of these amplitudes, and the phase determines the probability of detection at each detector. For clarity, imagine an experimenter standing near the first arm, holding a key, a device that can smoothly adjust the optical path length. By turning this key, the experimenter can decide whether all photons end up at detector 1 or instead all of them go to detector 2. That experimenter might conclude that every photon travels along the first path, since by adjusting the key, they can control where each photon is detected. Now, place a second experimenter with an identical key near the second arm. By manipulating that key, they could reach the opposite conclusion, that all photons travel along the second path. Based on this, we can conclude that each photon travels along both paths, because otherwise neither experimenter would be able to control the behavior of all the photons by acting only on their own section of the setup. The Mach-Zehnder interferometer shows that a quantum system doesn't obey classical trajectory logic. Before measurement, a definite path cannot be assigned to the photon. By adjusting the phase in the one arm, we control the detection probability, not by changing force, not by changing energy, but by changing the phase of the amplitude. This is one of the cleanest experiments revealing the depth of quantum reality. We are forced to admit that an indivisible photon somehow manages to pass through both arms of the interferometer. How does it do that? No one knows for sure. Some physicists deny that the photon travels along two paths. Others appeal to parallel universes. What really happens will be the subject of another video. Thank you for being with me on Bold Science with Firyuza. Subscribe, give this video a like, and I'll see you in our next quantum adventure.